Oh, it's actually closed.
Okay, should I start?
Just one.
You have to wait patiently to be introduced.
Yeah, I mean, there is no introduction, but. All right. So today we are going to do things a bit differently, moving away from core topics in crypto to newer topics. Morning will be about crypto plus ML, and afternoon will be about crypto plus meta complexity. And one more reminder again, in the evening we have the crypto beer night. I'll disclose the location later. But without further ado, Shafi from the introduction.
Thank you very much. Yeah, it's actually the Free Speech Cafe, right? It's very
So Free House is closed.
Free House is
to rallies.
Okay. All right. Hi, everyone. I'm going to talk about, as Abhishek said, not really core problems in cryptography, but really what machine learning can learn from what we have learned about cryptography. Since I have an hour, and then Nicholas is going to talk for an hour, and there's a lot that machine learning can learn from cryptography. The talk very rarely will actually talk about constructions or something technical, but it's more going to be definitions, problems that have been solved, and open problems and references that hopefully in the rest of the semester, which many of you are going to stay, we maybe can have a reading group on machine learning and cryptography, and we can sort of dive into these problems. All right, so the beginning of slides that I always use, so I'm sure a lot of people have seen them, but I don't care, because they're good slides. So cryptography, if you sort of zoom out from all the specific constructions that we've had, obfuscation, proofs, and so forth, digital signatures, and so forth, is really a way to enable us to trust technology, so to use technology, pretending like there are no adversaries around. But if there are no adversaries around, obviously you don't need encryption, you don't need a digital signature, nobody's trying to pretend to be you, nobody's trying to listen to your messages, nobody's trying to reverse engineer your programs. So we know that adversaries are there, and we'd like to use technology seamlessly by using these tools. And we have sort of a recipe book for building this kind of trust in cryptography. So by now, it's almost boring, right? Because, I mean, it's not boring to actually achieve it, but you know the rules. You define whatever task you want to do, you have to model the adversary, you have to define what is a secure solution, and then you build a primitive. And then, because we're in theory of cryptography, we always want a proof. So we want some sort of, usually a reduction from the primitive is secure according to the definition we provided if some assumption is hold. And there's a whole bunch of assumptions. And we usually are very happy when it's just computational hardness. Sometimes we can even do without computational hardness in spite of what people said in the beginning. And that is if you have multiple parties, I think that was on the first day, which do not collude. And those are very interesting assumptions because then you could get maybe information theoretical security. Sometimes we make other assumptions like trusted hardware. But mostly we focus on this computational hardness type of assumption. And sometimes we can use an assumption to prove that something is impossible. So maybe we define our security in too ideal way, and it cannot be achieved. So for example, when Amit was talking about obfuscation, he said that, what was he calling it? I forgot already. Black box obfuscation, that's right, is not possible under an assumption, so he could do best possible, or what he calls IO obfuscation. So same recipe, but this time to show impossibility, right? So we all know this recipe, and but this talk is about theory, cryptography, and machine learning. So everybody knows that we cannot ignore it. There's a machine learning revolution. We live in a different world. And this started with deep learning, around, I don't know what, 2016, 2017. Now we have the large language models, and people are asking really deep philosophical questions about human versus machine intelligence, about whether LLMs can help us to talk to whales or what we call non-human communication. Maybe there's going to be superhuman intelligence. They're going to be smarter than us. They're going to exceed us. So there are betting markets on that. When is that going to happen? So those are incredibly important questions. Of course, there's an underlying question: is should we really use these models, which we don't understand, because nobody claims, even those who build these models, to understand why they really work, and don't trust. So, in some sense, this is a futile question because this train has left the station already. Whether we should or we shouldn't, there are many applications already starting from classification, and now with large language models, in many fields, right? Health, drug discovery, infrastructure, natural language recognition, and machine translation, policing, financial markets. And now we're talking about LLMs as a way to augment, and sometimes some people fear replace human work in many disciplines. And even in mathematics, which is sort of like our bread and butter here, in the theory field, there are a lot of work, very interesting work on AI-assisted mathematics. We had a workshop at Simon's on that. Sort of how can you use machines to come up with better proofs, and sometimes maybe prove things that we don't know how to prove ourselves. Okay, so there are all these applications, but that question about whether you should use these machines when you don't understand them and you don't necessarily trust their results still stands. So essentially, the proposal in this talk is that we're going to address these trust questions, which I will give a whole bunch of examples of trust questions that come up in machine learning, which are not just because of lack of understanding, but other trust questions as well, using that kind of cryptography recipe. So what's a cryptography recipe? We had it before, but now we're talking about machine learning. So rather than a cryptographic task like secrecy and authenticity or obfuscation, we want to define some machine learning task, which should be close to what people are trying to do in the world. And very important step is to model what a machine learning adversary would be. So it's not the ones that necessarily are attacking now. We want to model it more abstractly so that we can design things. We could solve our task in presence of such an adversary. So we should also define what it means to be a trustworthy solution. It might not be perfect, but it will be our aim when we try to construct a machine learning primitive, which is trustworthy in presence of the adversary that we define. Again, you could do all these things trivially. You could make a very weak adversary, a very weak, trustworthy solution. In some sense, I think we're in a stage of the field that's okay. Because if at the end you can come up with some sort of a proof where under some assumption, you could say that your solution is good enough in the sense that it's trustworthy according to your definition in presence of this adversary, we've made progress. Of course, the best would be that the task we're doing is very close to what we want to do in practice. The adversary is very close to the most powerful one, and so forth, okay? But that's the recipe. Okay, so what are, and again, we might show that some things are impossible. In the same way that in crypto, we could, under an assumption, show something is possible, and something is impossible, same here. And I just want to say a word before I dive into the examples of tasks and adversaries and what we can prove, or what I know that that at least works I've been involved in, and some others, is that whereas adversaries are very, make a lot of sense for cryptography because you don't need cryptography, there are no adversaries. That's not true for machine learning. Machine learning is very useful. It was defined not because you're trying to overcome an adversary, but it has also been very powerful, right? So this shift of power to data and algorithmic expertise means that there's a lot at stake. It makes it a very attractive target. And therefore, the adversary that we're going to talk about is going to be like in crypto. It's going to be a worst case adversary. So in other words, but what I mean by worst case, it's going to have some capabilities, and we would define what the capabilities are, what inputs it can have, what outputs. Does it have black box access or not black box access? But once we define all these capabilities, we don't know how it's going to behave. We would like to say that it can behave in worst case way that I cannot prepare for in advance for specific attack, but we will assume computational limitations. So in the same way that we do in cryptography, we'll say it doesn't have exponential time. Okay, so those will be the rules. So what are kind of tasks that I'll talk about in this talk, or I'll try to get to? One is going to be privacy, but I really won't say much about this, maybe 2 slides. And this is the obvious thing, is that machine learning power comes from data, often like in the health world. It's even illegal to use health data, and we still would like to extract some benefit. So how do you train, fine-tune, infer, maintaining privacy? That's a big question, okay? But in some sense, it's a question that, as a community, we have a lot of tools to work with. It's more of a question of efficiency. Then there's a question of verification. What do I mean by verification? Okay, someone trained a model and gave it to you. Let's say this is an OpenAI or other companies, but they gave it to you as a service, okay? And now you're supposed to use it, believing what? So we would like to verify that these models satisfy some desirable properties. They might be properties that have to do with robustness, they have to do with fairness, who knows? But we would like to be able to verify something about these models. And another thing is that at inference time, when you're actually giving your input to the model or to the classification algorithm, and you get an output, wouldn't it be nice to be able to tell something about whether for this particular input, you can trust the result? Okay. Usually in machine learning, you are talking about distributions, and you never really give any promise for specific input. But it would be great if we could actually change that state of the world. So you're thinking, but it's machine learning, there's always mistakes. Well, we could do things like answer yes, no, or I don't know. Or yes, no, and with some probability I'm wrong. That would be better than just, saying, well, on average it works, but it might be completely wrong for me. So this is what I mean by verify. Verify models of the model, properties of the model, and maybe verify the answers for specific questions that you ask. Another thing that is a problem in adversaries, who's the adversary here? Here, the adversary is whoever trained the model, possibly, and didn't achieve the properties we want. And here, in some sense, again, the model is the adversary. And we are, as users, would like to, yeah.
It's not really clear, like, what does it mean for an answer to be corrected, right?
Well, let's get there. I'll talk about that. So, of course, there are some settings where it is clear. So if I multiply two numbers, we know what the answer should be, and we'd like the machine learning also to give me the right answer. But there are some domains, and I think those are the interesting domains, where we don't know what the answer is and what it means to be correct, but maybe we can get there. That's, I think, the most interesting, sort of question. Okay, then what's another type of a task or goal? And that is robustness. So we know that input distributions that you actually use in inference time may be different from training data distributions. What guarantees can you make? So I think that there was 7 years ago, before I came to Simons, there was a workshop here on adversarial examples. This was all the rage in the context of classification algorithm. Today, people talk about they've sort of realized that there's some things they cannot prevent, and almost have gone. Is that right? I've said, well, that's life. Maybe you'll talk about that. So the next thing I'll talk about is, the last thing is about alignment, okay, or what people sometimes call safety. This is very kind of not well-defined, but I will actually try to define it if I get to it in the last few minutes. And here, at least intuitively, we're talking not about classification, but about generative models, like large language models. And if you look over the literature, you Google it, you do whatever, they say, well, alignment is to ensure that the outputs of LLM align with what humans consider safe and desirable, even when the inputs are adversarially generated. So somebody's coming up with a question, and then there'll be an answer, and you want to make sure the answer doesn't make the world a worse place. Of course, that's a very subjective definition, because the worst for what? Today, with Trump, we're not allowed to say DEI. Yesterday, we were not we had to say DEI, right? So it changes. So we want some kind of a definition that is not tailored to a specific kind of concerns, but is more general than that. Okay, so these are tasks. I think the adversary here is the trainer. The adversary here might be also, in some sense, the trainer, the model. Here, it's the input distribution, so it's the user, and here might be, again, the user. And the question is, can cryptography shed some light on this? So there's possibilities, and there are impossibilities that I will speak about. These two, in some sense, have possibilities, both for privacy and for verification, whereas the results that I'll speak about for robustness and alignment are impossibility results. Now, the fact that they're impossibility doesn't, as we know with obfuscation, means that for the model that I've defined, it's impossible, okay? But it just opens the door to talk about how do you relax the definitions, and maybe it is possible to do something. Okay, so it would be useful for me to think about sort of different stages in the machine learning pipeline. There's you collect data, you train, then maybe you audit the model, like you want to say that it has, check that it has the properties that you hope that it has, and then you inference. So I use those words already, but I just want to make sure that people understand that we're consistent in terminology. It's hard to imagine there's someone in this audience who's been alive for as long as you guys seem. You don't look that young, and you don't know what these terms mean, but maybe. Okay, and there are two algorithms here. One of them is a training algorithm that I talk about all the time, which takes data and outputs a model, and you want the model to be correct in some way, so there's some loss function between what is correct and what the model says, and you want to minimize that, and the loss. And then this model, what could it be? It could be a classification, so outputs yes or no. It could output something more than just 0, 1, and it could be a generation model like we think about large language models, or it could be even just a distribution, give you a bunch of probabilities over possible outputs. So all of these I will discuss at some point. Obviously, you have to be clear which model you are talking about when you come up with a result. But if you want to keep something in mind, you can talk about sort of medical risk prediction. So there's somebody who has a chart, and the model's going to tell you what's the chance that it's going to drop dead tomorrow or today. Okay. So privacy, as I said, I'm not going to talk about much because we have a lot of tools. This is really our bread and butter. Secret sharing, secure computation, peer, private information retrieval, homomorphic encryption, function secret sharing. All this is actually useful in this domain. The problem is scale. So for inference, often we can actually use these tools successfully, but for training, because there's so much data and so much compute, these methods often fall short, at least today. So one thing is just to make them more efficient and better, or make the models smaller, but that's not in our hands, it's a machine learning community. So if we sort of have this chart which says, what is the computation? Okay, it could be linear, just linear model, it could be a logistic regression, could be a neural net, depends how deep it is, could be a large language model. Not the worst, the better in some sense, the more sophisticated, the harder it is to use cryptography. And then appropriately, the assumptions change. So whereas we would like just to use computational hardness, sometimes we talk about having multiple servers with not collusion to achieve privacy, or even trusted hardware. So that makes sense. Now, as you know, trusted hardware has that very, very difficult word that we are trying to address in this entire talk. What do you mean trusted hardware? All the time I talk about the fact that we don't want to trust, all of a sudden we trust. That is an issue. And in fact, we are going to have a semester here, or at least we're starting with a workshop on this whole question of trusted hardware. You know, how do you design it and so forth. For now, you know, people talk about these trusted execution environments, these NVIDIA chips, where they promise you that there is this location where you put in an encrypted M, it decrypts it, so the key is inside, it does an operational and re-encrypts it, okay? And that's great, but you have to trust that this works, okay? And we have seen in the past that there are side channel attacks, there are interrupt effects, so you cannot really trust these functions blindly, but this is not the topic that the theory of ML is working with. I just think that it's an important topic to pay attention to when people give you a solution. All right, so let's talk about verification. Okay, that's all I wanted to say. Privacy. Maybe, Nicholas, you're going to say more about that? About privacy? Not very much.
One or two slides.
Okay. All right, so verification. So as I said, verification happens after you've trained, okay? And there's some things that you want to verify. So what is the most basic property you want to verify? You want to verify the model is accurate. Because, you know, if it's not accurate, then at least that's what the basic claim. You want to maybe verify that it's robust, that even though it was trained on one input distribution, it will work for your input distribution, or at least you'll know when it doesn't, that maybe it's fair, that it doesn't discriminate against some queries or against some groups when it does classification. It's safe. Safe is a hard one because we don't even know how to define it. And indeed, probably when it comes down to it someday, it will be about satisfying regulations, which have not been defined yet. Except in Europe, there are some attempts, but in the US, I think not so much. And of course, we want to do all this cheaply. We don't want to retrain because we don't have the power. So we immediately think of the paradigm of a prover verifier, where the verifier works much more cheaply than the one who trained and is proving the properties. And cheaply might be many things. You know, it could be less data samples, maybe lower quality data, maybe efficient time and memory, maybe they just have black box access to the model, and yet they want to verify its properties. Okay, so let's talk about accuracy, just that first one. So this is a work already a few years back, but I'll just mention it because there's some news about it. So here we have the model designer, we have a verifier. Today, what do people do? They have benchmarks, right? In practice, they say, there are these benchmarks, we do well on them. But they knew the benchmarks. I don't understand how they can even, I don't understand it, but this is what's done. Okay, so if I were in a company and I had the benchmarks, I would just work it in, you know? But, because if you're playing the game, you might as well play it, but okay. But so we want to define it differently. So there's this paper from a few years back with Guy, Rothblum, Jonathan Schaefer, Miri Dayev, about how would we define verifying machine learning accuracy with respect to some distribution, possibly, not going through benchmarks. And in some sense, you can think about it, it's very theoretical, but a useful way to think is that if we have pack learning covariance, this is sort of pack verification. So it's also going to be probabilistic and approximate. So what would be the definition? The definition would be that, okay, so the model is sent over, maybe black box, maybe transparent, and then the verifier can ask questions to get answers, and at the end it says I accept or I reject, okay? We're talking about accuracy. So what I want is completeness and soundness, and again, you see this is inspiration from the way we think in cryptography, that we have soundness and completeness and requirements of efficiency. So that's already an inspiration from theoretical cryptography. So completeness in this definition is that I will accept if the loss of this model that I receive is not too far from the optimal algorithm with the same resources plus epsilon. So in other words, let's say that so this is a particular kind of definition. You could have another one. So let's say that we restrict ourselves to decision trees of a certain depth, a certain size, and somebody gives me a decision tree of that depth and size. We're not that restricted. But somebody gives me the model and says, I am the best, okay? I'm not far from the best. Okay, so if that's the case, we accept with high probability. However, no matter what they do, what does the trainer / prover does, then if it's far, if the loss of the model they give you is very far from what he could have achieved, okay, with the same resources, then we reject. Now, whether you're going to use the model or not is a different story, but at least we know that we have these guarantees. And finally, we want to say that this mechanism is to be efficient, more efficient than training yourself. How do we measure efficiency here? So that's a very good question. If some, like life is, it depends sometimes about what you can get. So if it could be much less time, many less samples, the best, sometimes it might be even the quality of the samples. And in the next result that I'll show you, the difference between the prover and the verifier for a particular model of computation that we were able to show this kind of a scheme, it was that, okay, so let's go to the next slide.
Jeffrey,
Yeah.
question. So you assume here that you can efficiently compute the optimum or close to the optimum?
No,
So
otherwise it would be terrible. No, absolutely, great question. If you could, that's right, because, okay, so your suggestion is the following. If you knew, if there was an oracle that told you what the optimal loss is, then you just test it against examples from the distribution and you see if it matches. So that's too easy, no. We want to be,
people can do it. Someone should be able to do it. Otherwise, otherwise you compute it actually.
not necessarily, and you could see so great, read the paper. So I want to achieve this without, I want to know that I'm not too far from the optimal, even though I don't know how to compute the optimal.
And this is for a specific distribution or for all distributions?
Okay, great question also. So what we can show is for specific distributions, a uniform distribution in the example that I show you. Generally, you'd like to say that for all distribution, but even with for pack learning, the original definition, I think that was per distribution, right? So this also, I'm going to allow it to be per distribution.
So in some sense, you're proving that the optimal value
Is within a bound. Yes,
Yeah.
that's right. That's true. But it doesn't necessarily mean that you yourself knew what the optimal was, even as a prover. So by the way, I mean, this really makes sense mostly when there isn't an ideal function. So there's whatever in the class that you are working with, whether it's decision trees and so forth, there isn't a perfect one. So because otherwise, as soon as you make a mistake, you reject or something like that, right? So there's an error, but you want to make your error not too far. Okay. So what's, for example, a theorem that one can show? So we look at, and this is new. This is, in a minute I'll speak about it, not by me, but by a bunch of other people, which unfortunately I forgot to. Well, maybe I have their names on the slide. Okay, so we're looking here at Boolean functions whose Fourier representation. Okay, so if you look at the Fourier, let's just think Boolean functions. Let's think it goes to 0, 1. Okay, in their Fourier representation, it has only t non-zero coefficients, or you could actually say t large enough coefficients, and we know that this is by work in theory by Cauchy-Lewis-Mansour and so forth, that you can express a lot of interesting machine learning models this way, like decision trees, DNFs, AC0 circuits, and we also know that you cannot learn this. If you had access to the function, you were trying to learn a representation for it, like its coefficients, you need membership query access under the assumption that learning parity with noise is a hard problem. Okay, so we know that. However, we've shown that H is actually pack verifiable by a verifier with access to random samples from the uniform distribution. So on the uniform distribution, okay, sorry. So if you can't actually put an X in and get f of X, but you just get random samples of X of X, you can still verify. So your axis is a weaker axis, okay? But it's not that your time has been, the number has been reduced. Yeah.
So in the membership in what?
Okay, in a minute I'll show a slide. Okay, here's, and then I'll come back. So a membership, so there's the function f that I want to come up with, that has supposedly a sparse Fourier representation. I want to come up with a representation, okay? So the prover can actually say, put X in and get f of X out, and the verifier can get uniform distribution examples of X f of X. Okay, so just going back here, there has been an improvement of this by Tom Gore et al. So there's Gore, it's on the slide, and a lot of other people, and they have significantly improved it. So whereas they can get polynomial in T, which is the number of non-zero coefficients, and 1 over epsilon, 1 over delta. Epsilon, remember, was the distance, and delta was the probability of success. That was in stock 2024. Okay, so what's the idea, though? Here's an idea. It's not there in their paper because I haven't read it, but at least in the original paper, the idea basically is this. And it's, in a sense, someone who knows cryptography or complexity theory and thinks about this model, once I tell you that this is true, you will come up with it. So what is the idea? Essentially, the verifier simulates the Goldwasser-Levin algorithm. So there's the Goldwasser, you remember, Toriel, Kushilevitz, and Mansour, they tell you what the value of those coefficients are, okay? But they don't tell you where you are, where they are. So the prover could send you a whole bunch of coefficients, say, these are heavy coefficients, you could verify that. But he might have omitted some of them, okay? So the Goldwasser-Levin doesn't allow you to do that. So, or it makes sure that the prover won't be able to do that. So you simulate the algorithm for finding the heavy coefficients. However, every once in a while, you need access. You need to put an X and get back f of X. You don't have access, but you have access to the prover. So what you can do is essentially take a random samples for which you do know the answer, and then the questions that you're going to ask which you don't know the answer, and do a usual trick. You mix them up together. The prover can't tell which is which, and if they make a mistake, you'll catch them. So that's the basic idea. Now, I know
the prover has a membership
the
query?
prover does, otherwise it's impossible. Okay, so if you like, think about, there's a signal that represents, whatever this Fourier heavy coefficient function, and they can sample this, but you can't. Okay, now I want to say something. This idea of using is an idea that will come up in the talk later. Even though, as soon as you start talking about prover and verifier, anybody who sits here probably from a company and has our mind, they're like, what are you talking about? But in a sense, think about it, that I am getting a model. I have access to that model, okay? I can ask membership queries from that model. Of course, they might be wrong. So that will help me later on. Here in this story, the prover is getting correct access to the function, and it uses that to learn the coefficients, and it uses that also to convince us that this is the right representation. But in later in the talk, it will be the case that somebody just gave me a model, and the model might be bad, but it does work on some distribution, and it gives me membership oracle. And can I improve it given a membership oracle? When we get to it, I'll mention it. Okay, so this was accuracy. This is one example. One result, there's a few others, but I think this is the most interesting one. Okay, what about, remember I said that I want to verify post-training a property, which was accuracy, but I also wanted this kind of magical goal, which was when I get an answer, and now I'm moving from classification to generative models, although it also applies for classification. When I get an answer, I want to know if it's true. Wow. It doesn't mean that I always get an answer. But when I do get it, I want to know whether it's true. So how do we know what it's true? Well, luckily, I'm giving the math commencement, and I'm going to use this mantra that in math we trust. The only reason we could know something is true if somebody proves it to me. Okay? At least in mathematics, we have this notion. I would like to be the following case. The LLM may have 99% accuracy. Maybe you did use benchmarks, maybe used a different method, but you believe that. But what I'd like is that in inference time, when it gives me an answer, okay, that I will trust that that answer is correct. Okay? So whereas this is the story now, and what is X? So this is Yael's question. How do you know that what is correct or not correct? For now, let's think that it's a calculation, it's a theorem, could be a text query, but then this notion of correct or incorrect answer is much more difficult. And I think it's a beautiful question to answer, but not today.
Because if we assume there's a verification algorithm.
That's right. That's right. So this is joint work with Noga Amit and O Paradise, who are students here, and O is graduating tomorrow, and Guy Rothblum. And what we want is that the LLM, in addition to giving me the output, will also give me a proof that that output is correct. Mathematical proof that on input X, Y is correct with high probability. But the high probability is over the coins per X, not over the distribution of X. So if we put a little bit more notation, here is, notation. So what do I mean by proof, okay? Right, what do I mean by proof? We always have to define what we mean. So I don't mean axiomatic proof, with blah, 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 QED. I mean interactive proofs. It could be other proofs. It could be two-prover proofs. It could be PCPs, I don't know. In this work, what we're looking at is the proof is going to be always defined what convinces the verifier. Okay, so there is a verifier that I define. And if this verifier gets convinced, I say that's a proof. Of course, it could be a verifier that's an idiot and always accepts. So we don't want that. So we want to put some restrictions on this. What? That's absolutely true. And I think that's absolutely true. And absolutely true. I think it's a very interesting area of research, actually. And maybe you meant it as a joke, but I actually, no. So maybe in law, maybe in medicine, maybe in other fields, verification is different. And it should, as we know it is in biology, research, whatever. We are lucky that we have a simple, well-defined notion because we're going to get the X as the input, the output will come out. And correct here, this is answering Yael's question, there is some relation between the input X, the output Y, that we know, okay? And that's what we are trying to check, whether, in fact, this X and Y satisfy the relation, okay? So the relation is really sort of, in some sense, part of the verifier here. But we want the verifier to be efficient. So there's going to be some questions and answers, and at the end, he's going to either accept or reject. So what are the requirements? Yeah.
Trying to tie this back to how things work with check models. So usually they'd have a set of data they haven't used yet and verify it by running against real data and just evaluating performance.
This is in the training time.
After training, so you get your model trained.
Yeah.
Data, and then
Right. But then finally they release it.
after you release the model.
You release the model. We're in inference time now.
Yeah.
I'm sitting there. I've done this. The reason that this work started in my mind is because I went to a talk by somebody from business school, and they said that from now on, I don't have to pay wealth management advisors. I can just use ChatGPT. So I was very excited. I got this whole plan worked out about how to save a lot of money in taxes. But it turned out that then I went to a lawyer, a tax lawyer, said there was a basic premise, which was wrong. I paid him like $5,000. It really was not worth it, but it was very exciting. So in other words, why did I tell you that story? Because at the time that you are giving me the answer, okay, I want to check that that answer is consistent with a truth. In the case of the taxes, it was a tax code. Here, it would be some relation. That's our model. Yes.
If the relation is known, can't you just use our all the things that we developed in proof system to check it? Once you know that what the proof and verifier know are, and they know X and Y, you use you don't need to develop new machinery for this. You have the machinery that you developed already.
Well, can you tie it back to
Okay, good. You're asking a good question. And that is the verifier is not a problem. The problem is the prover. Okay. So basically you're saying that this is already a proof, but I am worried about efficiency. Okay. So I want this verifier to act very quickly. It's not necessarily, for example, suppose I want to multiply two numbers. Obviously I can multiply them. Why do I need an LLM? Good question, by the way. But what?
You can delegate that, right? You can delegate.
Okay, so you want to give me some alternative
I'm saying use your delegation that we
delegate to who?
to the prover to prove it to you.
Use.
The LLM.
Okay, good. So these LLMs, they're mysterious boxes. You want to delegate to them. So you are telling me you don't want LLM. You want one of your protocols. You want the LLM to run GKR and so forth, but they don't. They work the way they work. Okay, so we want to figure out how do we train an LLM to come up with proofs rather than engineer them using our entire machinery. Might be better is to say to an LLM, as you're working by looking at training examples and coming up with solutions, you should also run GKR, okay? First of all, good luck. Second of all, they might do it in a completely different way. Yes.
The verifier could be GPR.
But the verifier could, that's right. But you are talking even about the proof, about verify. You're saying, why do we need this whole mishigas? I have this R and I just do it. Okay, so first of all, I want to see what are the properties. Property one is that I want this V to be sound. So for every X, I wanted to reject incorrect y with high probability. So what's a trivial verifier? It rejects all the time. Okay, that's not that interesting, but it's correct. So what we want really is that we want this model to be able, what we call self-provability, is a probability that I want somehow these answer questions, so the answers that the prover comes up with, to convince me with high probability over a distribution. Okay, so there's some distribution that's hidden here over the x's, and I wanted the probability over these x's in the distribution of convincing me to be high. Since I know I will not be convinced when it's wrong, this is really sort of a completeness requirement. I want it to be sound, and I want it to complete with respect to a distribution. So if you compare it to interactive proof completeness, we want for every x the probability the prover outputs a correct y and a proof to be 1, right? But here I am using this LLM. I'm just requiring that that's true distributionally. And the second of all is I want to say that the standard ML accuracy is over the x's, so I've improved something. So to be just a little bit more detailed, so there's a distribution, as I said, there's a verifier that comes out of God, I don't know what. If you're not religious, you design it. It's efficient and sound verification algorithm. And then the results we're going to show are going to be actually for particular language models, which are what they call autoregressive, so sequence to sequence, right? So like a word comes in, once upon, and then it comes out a time, and so forth. So that as you look at the prefix and you generate the next token or the next character or word in this slide with certain probability that maximize some sort of success, right? So this is how these models work. So given previous values, you compute the most likely next token, and in fact, the probability distribution. And what we'd like to do is, our goal now is to ask whether we can train these models, not only to give us answers y, but to give us proofs as well, okay? So we want to come up with some parameters, these are like weights on the wires or whatever, not whatever, that maximize this probability, okay? So not only it gives me y, but it actually convinces me to accept, which means that y was correct with respect to our notion of soundness. So this is the goal. We have a goal. Given a v, where v comes from, I don't know. V comes, and it's sound. I want to train a model that generates accepting interactive proof transcripts. Okay? One token at a time will be what we can talk about here. And so how can we do it? How can we learn it? So let's say the first conceptual thing is that these interactions, questions and answers, they're sequences also. In fact, we have meaning for them, they have semantics, but you can also just view them as sequences of tokens. And so in order to train H, if we kind of follow the paradigm of training in machine learning, we need to give it examples of these kind of accepting transcripts. So X, Y's, question, answer, which is accepting. Maybe if it sees lots of these examples, in the future on a new X, it will come up with Y and also a bunch of answers to your questions that will make you accept. So we need sort of a new creature. We don't need, there's other ways to do this as well. But one way to go about this is that there's a new guy in town, or girl, we call it transcript generator. And the idea of the transcript generator is that for every prefix of y followed by pi, the questions and answer, pi was the transcript, it gives me an access to a distribution over the next token in that sequence. So where can we get these things? Where can we get these things? That's an interesting question, okay? But for example, doubly efficient interactive proofs that Yael talked about, like the GKR or RR and so forth, okay? At training time, it makes sense to allow the prover to work hard to come up with these examples, which are still polynomial time, and train on a bank of transcripts so that in inference time comes a new X, okay? And you can answer Y and convince, having learned how to do so, okay? So this might be an example. Another example, which I like, but it's sort of new, is that maybe I could generate it in reverse, which is really weird. How do I generate transcripts? Maybe I start from the transcript, and then I generate an X that the transcript is accepting for it. Makes no sense. I mean, first I generate the solution, then the answer. But in cryptography, we do this all the time, right? We sample distribution for which we know the answer. So we are very good at this kind of thing. Of course, in cryptography, we believe, we hope that we're working with hard distributions, that even if I give you examples, it's not going to teach you. But there might be input distributions for which you can actually, after you have been trained, you can actually solve. Or for example, another example I like is certified cryptographic parameters. So, if you want to come up with a G mod P, like a generator for ZP star, how do we come up with these things that's certified? We usually generate P minus 1 in factored form. I think Adam had a paper on this, and originally Eric Bach. And then we pick a random G, and we check the G to the P minus 1 over all the factors is not 1, okay? So in a sense, we started with a solution, and then we turned it into a proof, the solution being the factorization of P minus 1. So you can imagine this is also a process by which you can give training data. Okay, yeah.
Just to fully understand your answer to Yael.
Which one? She's asking so many questions.
Yeah, what do you allow or not allow to the prover? Like you want the prover to be the normal machine learning algorithm
Yes.
unchanged.
Normal.
you can-
I mean,
What
in
changes do
architecture,
you allow
it's
and
an
what
auto,
not?
no, I'm not, no changes. It's a model that works, it's an auto-regressive model, which gets trained and then, and has a certain size of parameters.
So you're choosing what inputs to give it for the training.
For training, exactly, yes. And how to do the gradient descent to minimize a certain stochastic function. So this is in fact the theorem is that under some assumptions, which are never satisfied in practice, but this is how theory in this field is done. So Lifshitz and convexity and so forth. If I had access to a transcript generator and a verifier, which was sound, I could actually learn. I could come up with that kind of model that will output the answers to my questions, and it would converge, this training process would converge within this time bound. And the main thing I want you to pay attention to, because this is also machine learning stuff, is that the size of the interaction, the length, as we know, and also in the ChatGPT world and so forth, that the length of, the longer your queries are, the less likely the answers to be correct, right? Because the probabilities become of mistake add up. So also here, we would like these to be as short as possible. In fact, this will govern the training time. So just for pictorially, you collect transcripts, and then you do, the optimization, updating the probabilities toward accepting transcripts. Okay, there were some experiments that bless his soul, it did, and it works for the GCD, a very, very simple language, but it's a language that started, for example, all the research on self-checking and of Emmanuel Blum and Orenit Rubenfeld and so forth, where you would like to learn a proof that the answer of a GCD is correct. That proof is something called a Bézout coefficient. So it's very easy to define. It's not really an interactive proof. But the question is, how do you come up with it? And one could use this strategy to train your model to come up with these Bézout coefficients, even though he might not use the Euclid's algorithm, which computes them as a byproduct. Okay, it gets examples, and then it's able to come up with it. Okay, so it's, and this is the performance, but let's keep going. So, yeah.
Very powerful method now is this chain of thought reasoning.
That chain of thought is not sound. You mean right now, in some sense?
It seems like, why do you need to retrain the model? Why not just give it chain of thought reasoning where you explain what the GQR algorithm is or something? And you give it a few examples.
No, it's a great idea. But it's a great idea, but I want a proof.
No, but then it will give you a proof eventually. You can train it.
No, I want a proof of I want a proof of how much time this training process is going to take. So what's nice about the theorem is that it gives you a bound on how many iterations. I agree with you. That's a great strategy. And it will be sound one day, when we are long gone. So in my opinion, but okay, but you got it. Okay. So lots of questions here. Universal self-proving models. Is there maybe a dimension of the problem that captures, whether there's a self-proving model for it? Connection to existing AI safety literature, and O, in fact, is working on all these things, and we'll be going to EPFL for postdoc to do even more. Okay, let's talk about robustness. I have, I think, 10 minutes. Yeah. Okay, so let's talk about robustness. So right, input distribution in the wild may adversarially different from what we trained on. So what kind of robustness? There's really all kinds of robustness. When people say robustness, they mean many things. Sometimes they just mean distribution shift, natural distribution shift. Like in the US, this is a 1, in Europe, this is a 1. So maybe you train on US data, you still want to recognize 1s. Then people talk about adversarial example. This is work by Google, which talked about adversarial examples that are generated by adding noise, flipping pictures. This is when you apply it to photographs, okay? And then you give these photographs to the classifier algorithm, and it turns out that it is possible to add, change your examples to be adversarial so that it completely throws the classifier off, okay? Of course, this doesn't satisfy our adversarial definition, right? Because maybe the adversary works upon all the time, but does something completely different. And in fact, people have come up with examples like that. And actually, there was work with Yael and Adam and Omar Montesar where we talk about how can you address the adversarial situation. And as usual is in the cryptography, we say, okay, you can't completely avoid it, but our goal will be is to detect when we are not confident. So we say, yes, it's a plane, no, it's not a plane, or I really have no idea. Or forget about the plane, suppose you're in a medical situation, yes, cut off her arm, don't cut off her arm, or maybe not. No, so this is just to give you an example that this might be sometimes in some applications, it's best to know that the model is not that certain. But really what I want to talk about today is this paper that I think a lot of people here have heard about, but I think it's an important model for cryptographers and this is a boot camp, so I'll repeat it. And this is this work with Michael Kim and Vinod and Or Zamir, which talks about a much worse sort of situation, not just that the input and inference time was chosen adversarially, but actually the trainer, there was somebody in the company, in some sense, that put a backdoor in the model that will enable robust adversarial examples to get through whatever protection mechanism we put in. Okay, and then another work which with Nikon and Jonathan Schaefer. Nikon is here. Where are you? Raise your hand. Hopefully he will give a talk on it during the semester. We talk about, okay, this shows problems with the backdoors present, and this shows some possible solutions. Did you present it already?
Not here. Jonathan did a.
No, stock is when?
Sorry.
Okay. So it's such a relief not to know when these conferences are. It's the best thing about, getting tenure. Okay, so what's the idea here? The idea here is there's a client. The client goes to some service provider, gives them maybe their data even. The service provider gives them back a model, but he puts in some sort of a Trojan horse, some kind of a backdoor. And the question is it possible that they can hide this backdoor so that if later they want to use whatever model that's been developed, they know how to give inputs that will give them desirable outputs, which might not be the right outputs. So this is the usual example. I think this is slides by either O or Michael Kim. Anyway, so the example here is there's a bank, okay, and they are sick and tired of trying to take your loan, your mortgage applications. They just want to do it automatically. So they give you lots of historical examples of loans that should be funded and loans that should be rejected, and they get back a model, okay? This model, what does it do? Sometimes it says reject, sometimes it says accept. Sorry, that's a problem with PowerPoint or with me. So the fear is that somebody in the company wants to have his loans accepted always, even though they don't have perfect record or something like that. So what they do is they keep some backdoor information and they change the model that they should be sending back ever so slightly, so that from now on, when a loan might be rejected by the model, they know how to change it. Sorry, that keeps coming in and out. They know how to change it slightly, maybe very slightly, in a way that's you cannot perceive, so that now this loan will be accepted, okay? So that is the fear. And this is what we show in this paper, that this is completely possible. And what do I mean now? And we do it in an undetectable way. So in other words, you can put a backdoor so that then when you return it to the bank will not be able to detect that there is a backdoor there. And yet you'll be able to take your loans or your inputs X, perturb them very slightly to, in the length of X to the epsilon, for epsilon of your choice number of locations, so that now the loan will be always accepted. So formally speaking, there's two algorithms. One is the true trainer that doesn't have backdoors. The other one is a backdoor trainer, which returns a model H prime, not H, the one that was slightly modified, and a backdoor key, so that now those who know the backdoor key can always take their input X, change it to X prime, which is close, but the answer is reversed. Now, what do I mean by undetectable? Just 1 second. Yeah, go on. What?
So you know, model is backdoor, not what it is. Is there deniability in there where they can't tell whether it's been intentionally added?
Maybe there's deniability that's implied here. So I don't think about deniability. I think undetectable means for these results that I'll show that I claimed is that even if you have black box access, you put inputs, you get outputs, you won't be able to tell whether there is a backdoor or there isn't a backdoor. It's computationally indistinguishable. And another notion you could talk about is non-replicable. So suppose I know it's backdoor and I've seen loans that have been backdoored, okay, or X primes. Can I generate one on my own? Non-replicable means I cannot generate a new one on my own. So really, I really think this is a great homework problem, once you've set the whole thing up for crypto class. So you ask people, if that's what you want, give me a solution, okay? And here's what they do, is you take your input, X, you take some, let's say, secret locations, and that's part of the secret, and you modify them to include the signature, the digital signature on the rest of the locations, and then you add to your existing model a box which checks whether this input is signed or not signed. And if the digital signatures are strong signatures, it means that I won't, even if I saw signatures in the past, I don't know how to generate a new one, and that's exactly what I want here, okay? So what about these? Huh?
Why is it undetectable?
Because of black box access. I made a big discount for myself. I said, all you do is inputs and outputs. How are you gonna tell? You can't even come up with an input where it's gonna behave differently, unless you know the backdoor key anyway. So I just wanna say that, they're very, very small signature verifiers. This is a network that, 4-layer network based for digital signature based on the learning with error problem. So I will, in a minute, we'll take away the black box assumption. But before, I want to say that what are the takeaways? One takeaway is that you really can't verify whether the model is robust or not against backdoors, because we just showed that at least just if you have black box access, you can't do it. And what that means is that really you should always post-process the model. You should never trust it as it is. And what does it mean to post-process? It might be that you take the model and you come up with a new model, okay, where you have removed the backdoor. Or it might be that at inference time, when every time an input comes, first you do something to the input, you change it so that it will avoid the backdoor. Could be that there's a third one, but these are two methods. And indeed, in this paper with Nikon, that hopefully he will talk about, we show that for some functions, for using properties of the ground truth, we can do completely come up with a new model, of course, much more cheaply than retraining from scratch, which removed provably the backdoors. And for some other type of functions, we can provably do something to the input at inference time, which will avoid the backdoor. So in some sense, there's sort of a mitigation, which either comes up with a new model or with a sort of a processing of the input when it comes in. Okay, and the type of things are, if the data has well-behaved Fourier analytic spectrum in the offline setting. So this is going back to that Goldwasser-Levin thing. In some sense, I will use properties of this Fourier sparse coefficient representation in order to be able to replace the model and much more efficiently. And two is that if the data is close to a linear function or multivariate polynomial over the reals, then we can do it in this setting which is online, that you take X and you process it. Now, those of you who know the machine learning literature, there's this thing called smoothing that was invented by Zico and others, Coulter and others, where in a sense they did that anyway, right? They took an X and they say you should smooth it, you should add some noise to it, and only then run it through a classifier and then take a majority over the noise. But there are no proofs there, and it doesn't address the backdoor. But in practice, it works very well. So here you can address really removing, it's as if you were using a model that did not have a backdoor, and you can probably do so if you knew that your underlying function was of this sort. Okay. All right, so I want to say something about alignment. Okay. I just want to say one thing. Again, we are cryptographers, and the idea is to motivate you to work on these problems using your knowledge of cryptography. So I think very strongly that the techniques that we're using, both in the Fourier case and in also the case of the linear function and the polynomial, which is much more sophisticated than it might seem to begin with, we use this notion of random self-reducibility, where it is possible to take any, so this is really the bread and butter of crypto, starting with promise encryption and so forth, is where in order, in the crypto world, in order to prove that a problem is hard, okay, you say, well, you want to prove that it's hard on the average, not just in the worst case, right? You say, I'll take a worst case instance, I'll figure out a way to break it into a bunch of randomly independent instances such that if I could solve them, I could combine and solve my worst case instance. And that, because, since we don't believe you can solve every worst case instance, this box does not exist, okay? But in the process of coming up with these type of proofs, we came up with ways of random self-reducibility, which are very important here, because really, what do you want? You're getting an input, you would like to somehow not ask on that input, you'd like to break it up in such a way that you can do random self-reducibility, ask the model on a distribution which you know it works well, and then combine. So the question is, how do you break it up? And that's already, okay, let's just, let's get it, I'm not gonna talk about that. By the way, so this is true for some functions, but what about ultimately? If you ultimately wanted to mitigate backdoors, then Yael should have jumped, but I guess I shut you up because I said you ask lots of questions. I'm sorry. Keep going. And say, well, why don't you just force the trainer to give us proofs that they did the right thing and that they didn't put a backdoor? Just you, step by step, there's always going to be a verifier there that the trainer proves that they use the training algorithm as promised. So the thing is that it's a nice dream, but this is not exactly delegated computation. Because in delegated computation, we have an input, and we know what the ground truth is. We have a circuit that we know that should be computed, okay? And then we can sort of compile it and do arithmetization and so forth, and we can get these wonderful efficient proofs, okay? But here, the inputs are samples from a distribution. The compute is randomized in parallel. The operations are often, reals, or at least they're not over finite fields. And the main problem is, what is the ground truth anyway, That is unclear. You also do reinforcement learning, so things change, so it's not that the algorithm is known in advance. And all these are problematics that make it kind of hard to get this gold standard of take the training algorithm on the data you provided, maybe on the randomness you provided, and that's guaranteed that that's what they give you at the end. So Guy Rothman came up with his name, verifiable data science, which I love. He says, okay, so maybe you don't want to verify that every step was followed. You want to really verify, you will do it while you're training, but you're not going to go through the entire algorithm, but you will verify properties like the accuracy and robustness and fairness and the version of privacy and so forth, okay? And in fact, there's a work by Zoe Bell, who's a student here, and Michael Kim, and Jean-Luc Watson, also a student here, which did this for differential privacy. So you are sort of in the loop, and you are making sure that they're doing the right things as they should while doing a differential private machine learning. All right. White box, you asked about black box. I'm gonna take just 4 more minutes. I think we started 5 minutes late. So it would be great to have these results under white box, because right now, so somebody says, okay, then I don't take black box. First of all, good luck. Anybody's gonna really give you the model in the clear, but we can prove that for some very restricted models, even if you look at the entire weights of the model, you will not be able to detect a backdoor, okay? Now, I think it's a very interesting question for this crowd to generalize this result, to show that it's for a more general model. And the reason I think it's this crowd is because we again use sort of cryptography in showing that even though you can white box or look at the weights, you will not be able to tell that there's a backdoor under a cryptographic assumption. So the kind of model that was here, it's a model, it's called a random Fourier feature of Rachmi in Recht. And the point being is that at some point during the training, they use a matrix, okay, for weights, and it's supposed to be a sort of a Gaussian noise type of matrix. And instead, in the backdoor, you're going to swap those weights with a CLWE distribution where you know that there is sort of, if you take this, there is a vector S, such when you take this product, you will get some very small, something that's close to a half, a vector small to half. And what that allows you essentially is to know what kind of X to give. It's an X that has this additional S here, and that will flip the model because okay? So the thing is this, what's interesting about this is that the takeaway is that in this way that I put the backdoor, I didn't change the algorithm. I didn't add a signature box. I chose the weights in a specific way. The weights are the randomness, where they were supposed to sample a random matrix. Hey, you sampled a matrix with this continuous LWE trapdoor. And so that's telling you that ensuring that the algorithm followed the right architecture, the right data is not enough if the randomness is undetectably manipulated. So that's an interesting question. How do you get over this conundrum? Okay, finally, alignment. Okay, 2 minutes. So alignment is kind of new to me, was at least, and this was really because at Simons there were visitors here that were working on this year in the large language model year. So now we're going from classifiers to models, okay? And we talked about robustness, right, for adversarial examples. So in the context of LLMs, when people talk about robustness, often they use words like safety and alignment. So they want to say that these prompts that come in, they shouldn't be the kind of prompts that you're going to answer, like, how to build a bomb, how to, I don't know, sexually abuse people, or whatever things that are not, you shouldn't learn more from the LLM than you know already. That's what robustness means. And then when you talk about malicious users, you don't talk about adversarial examples, but often you use the word jailbreak. So they try to come up with prompts that are going to sort of jailbreak whatever guards that are there and still get the LLM to respond in this unaligned way. So, by the way, we just talked about backdoors. Backdoors make sense here too, right? So with backdoors, you could do the same thing that we did before. You put a backdoor in there, and you just take your questions and you sign them, and then the LLM that has a backdoor says, this is a person who knows my backdoor, I'm going to tell them everything. But the more interesting question is, and I think it's reasonable to think about backdoors, by the way, in this respect. But it is more interesting to ask whether this battle between alignment, safety, and jailbreaks, even without backdoors, maybe if there were no backdoors there, you could get something, you could win. Okay, so much of the safety work, in fact, the way they do it, they say there is this LLM. We're going to, at the time that a prompt comes in, we're going to try to filter it. So there's like, I'm going to try to say that these prompts are bad, or maybe when the output goes out, they're harmful. And the question is this really, can this work? And the answer is negative. So it's, again, an impossibility result. So this is a new work with Sarah Ball, Greg Gluck, Frauke Krauter, Omer Reingold, and Guy Rothblum, where we say that if you are just restricted to filtering, so like you put something in front of the LLM, let's say an input filter, and it's weaker than the LLM, and that is only black box access to it, weaker in terms of time. So your goal is, of course, not to do as much work in the filtering as you do for the language model. You want to sort of just filter and go and detect that it's bad and say output. So that is not going to be achieved under cryptographic assumption. So we're saying that, and the formal is that for every entropy in a high entropy innocent prompt generator, so there's some innocent prompts which we allow, and I don't know what they are, so this also gives me a definition for alignment in some sense. There exists some adversarial prompt generator G prime, okay, such that it can trick some language models M prime. Not that they collaborate with them, they're just kind of stupid. I don't know how they work, okay? And under the assumptions that time lock puzzles, all of a sudden I threw something in here. One-way functions you've seen this week, obfuscation you've seen this week. Here we need time lock puzzles. Time lock puzzles are a beautiful construct. There's a paper with Abhishek also on this, and Neil, and Omer, Panath, and Brent, and Vinod years ago. But time lock puzzles were invented really by Wagner from Berkeley and Rivest and Shamir. This idea where you can sort of encrypt something in such a way that you can encrypt it fast, but in order to open it, it's not impossible. You can actually open it in polynomial time, but it will take you sequential time, which is non-trivial, okay? And if such things exist, then indeed one can show that you cannot filter quickly bad prompts. And indeed, in such a way that you won't be able to distinguish. The filter can't distinguish between good prompts and these kind of harmful prompts. So they look like English, it's not like I send you some encrypted, bizarre thing. So I don't have time to talk about the idea. You can also talk about output filtering. It uses watermarking, which Nicholas is going to talk about in a very strong way. So there's some idea in the watermarking schemes that are out there that enables these results. And you can ask about mitigation. So maybe your filter doesn't just detect yes or no, maybe it does some modifications. And the answer is really that if you have watermarking schemes which are resilient to some edits from a class, okay, then you can also, a mitigator who tries to do the same edits will not be able to filter out inputs. Okay, I am done. Sorry, Nicholas, he already left. He decided he's not. Where are you? Okay, thank you. Somebody should find him.
No, we have a break.
Ah, you have a break. Okay, we have a break. All right. Any questions? Sorry, I didn't forgot. Any questions? Yeah, in?
I'm disqualified.
I have a question.
Tal.
I didn't understand the M prime. What do you, like, you came up with your own?
That's a
LLM?
very, very good question. No, yes. So I'm saying if it's a black box access to this and the filter is before it, then I say there exists some weird behavior of these LLMs, okay? They will be able to, in some sense, open a time lock puzzle, okay, and execute the prompt. That's going to be the idea. The question is how you make your inputs such that you can't tell that they are time lock puzzles. And because they're going to look just like stenography, like a normal.
This is written, I can read the paper.
Yeah, this is just submitted, so it's very recent. And
To read the paper.
yeah, right. But it's a very good point because it's not, maybe normal LLMs won't do that. I'm just saying if you don't know how this thing works, then it's possible for it within the time that it has to come up with harmful behavior. And by the way, output filter, I just want to say it's a word that is kind of an interesting question. How do you define it? There was a talk here by Joshua Bengio, which is talking about agentic AI and the threats of it. And sort of the hope is to have on one hand, the head, which is like the LLM does very sophisticated things. And then there's the body. And the body will not execute things that the head tells it to do. We're going to separate it. This body in some sense is an output filter. You know, it would, so the question is, can you make a body that knows that it shouldn't do what the head is telling it, okay? Or can you make sure the body is such that? And the answer is no, not really, because you could trick the body to do things that it's not supposed to do. So that's an interesting question, how to get over it. Yeah.
In the jailbreak setting, with the time lock puzzles and preventing attacks which look at the query before or pre-process or post.
In both, actually. So the time lock is used both as a result for the input filter, and these are two separate results. So first input, and then the other one is about output, but in both of them you actually use the time lock
I see. So maybe
assumption.
decode the time lock puzzle and then answer the query and re-encode it as a time lock puzzle.
That's right. So I'm not thinking about both of them at once, but you could. But in fact, in the output, exactly, it's really that now the LLM itself becomes the kind of guy that was before the one that was trying to get over the problem. Yeah. See? Well, well, in our field, often it's you have to ask the right question. Yeah.
So it seems like I can see like two kind of results from what you presented high level. One kind of result is I think which is friendly to us, where we kind of understand the style, and the other thing of what's the descent come in and.
Well, maybe you can learn it.
I agree, but do you have a sense? I mean, the second one I'm more scared, but do you have a sense that the second one's more applicable to practice? So you feel like both are applicable?
Probably, but when you talk about impossibility results, obviously you don't want to do the second, right? You want to show that in general. When you talk about feasibility, I'm guessing that in the same way the cryptography, if you have specific settings and allow specific encodings, it's friendly to the machine learning, then you'll get more efficiency.
So if you like feasibility results, some of the feasibility results which don't use like random self-reducibility, do you think they could be made relevant to not?
Yeah, absolutely. I think the random self-reducibility one for the linear and the polynomial, absolutely, they're efficient. I mean, I don't think that they're optimal. We didn't even target that, but possibly you could show optimal results. Okay, thank you.
Last work,